This is the solution to the hockey puck problem found in the text. So, we are looking for mu k. We always have to think ahead of time. Mu k is going to come out of a force equation. So that means really we're looking at F equals ma types of problems. So let's draw an F equals ma setup for the hockey puck. There's the ice. Here's the puck. It's mass m. That's all we know. Let's set up some axes like this. And furthermore, let's say, so we can keep it straight, that the puck is moving this way. So remember, y and x do not tell you which way an object moves. We're going to just write moving for our own knowledge so we know how to draw a friction force. We'll still use our axes for positive and negative. So the forces that act on the puck. N, the normal force, mg, and the friction force, Fk, this way. Notice, there is no force pushing the puck forward. That force is already gone. The stick hit the puck is now moving. We are analyzing it when the stick is gone. So it's no longer being pushed forward. It is going forward on its own inertia. So this is our setup. How are we going to get mu k again? Fk is mu k times n. Again, mu k is Fk over n. We need Fk, we need n. Fk is along the axis of motion. Let's do this. Sum Fx equals max. So let's draw the forces, or write down the forces. There is only one in the x direction, since it points opposite to our axis. Negative Fk equals ma. So what is Fk? That says Fk is negative ma. Well, you can't go any further, but that's what it is. That will go in here eventually. There's no numbers, that's what we can leave it as. Well, we're not changing our approach. We look at the x, then the y. Sum Fy equals may. N minus mg. Once again, the acceleration in the y is 0. It's not crashing through the ice. It's not flying off the ice. It is not accelerating vertically. So n equals mg. Now again, that's going to go here. So let's see what happens. You have mu k is Fk, negative ma over mg. The m's cancel. You end up with negative a over g. This is why I always have been saying, put numbers in at the last possible instant, because if you decided ahead of time you don't know the mass and it's not solvable, you wouldn't have even attempted the problem. This shows, for this problem, the mass has no bearing on the solution. In fact, mu k for this problem depends only on g, which is 9.8. We don't use negative g for this. And the acceleration. So this tells us we need to know the acceleration of the puck. Well, we can't use F equals ma to get it, but we have a bunch of motion information. So let's solve a motion problem to get a. We must use the same axes. Start, end. You were told 20 meters per second, and it's going to stop. And you were told the distance was 120 meters. So our goal is to get a. V0, 20 meters per second. V, 0 meters per second. So we know V bar, 10 meters per second. We know delta x as 120 meters, and we want a. The other unknown term is t, which we shouldn't need. We do have an equation to get a out of this. V squared, equals VO squared plus 2a delta x. So a is V squared minus VO squared over 2 delta x. We have all those numbers. Just substitute them in, and you will end up with a as negative 1.67 meters per second squared. This makes sense. Based on our picture and the way the problem is set up, the acceleration is negative because it is slowing down in this case. The negative does mean slowing down, and it makes sense. Now that we have A, way back up here into substituting. So mu k is negative A over G. So mu k is negative of a negative divided by 9.80 meters per second squared. Negative of a negative makes it positive, and you end up with 0.170, which seems quite reasonable. Not a large mu for a puck on ice. It also is in line with the allowable values for mu. You can't get a negative mu that makes no sense. Mu has to be between 0 and infinity, any positive number.